everyone. I'm Katie. I'm a final year PhD student at the University of Cambridge, and I'm glad we started talking about humans at the end, because that's what I'll be talking about primarily. My background's in computational cognitive science, but I've been very excited about mathematics over the course of my PhD, working with Tim Gowers and others at Cambridge. So I'm going to be talking about how we decide what games to play and what mathematics problems to solve, so I'm glad Mike brought up interestingness. As we just heard, there's been tremendous progress in mathematical reasoning for across a range of areas, from geometry to some great work from Albert and others on auto-formalization, to other techniques using search-based approaches, Project Numina, and beyond. But as Mike brought up, it's not just about kind of how we solve mathematics problems. We also decide what problems to solve in the first place. And we've been focusing, as Mike was saying, on problem solving, not those decisions. For instance, think about Andrew Wiles deciding to spend a large part of his lifetime on proving Fermat's last theorem, or a great quote from David Hilbert that if he were to awaken having slept for 1,000 years, that his first question would be, has the Riemann hypothesis been solved? We spend a lot of time thinking about what problems to even solve and are fascinated by the problems themselves. Or a great quote by Michael Atiyah that the art of good mathematics is kind of having to identify interesting and solvable problems in the first place. So what is going on in our heads when we decide whether a problem is worth solving at all? A lot of today, you'll hear about mathematics and language models, but what I hope this talk kind of covers is that there is humans are key in that loop, and we are doing interesting things when we think about mathematics, when we learn mathematics, when we decide what problems to work on, what games to play. And I think that should be more, or have a bigger focus within the AI and mathematics community here. So there's been a lot of work in modeling minds in computational cognitive science with mathematics, thinking back to Turing's great work, where he was really thinking about what it takes to model minds. Some of the earliest work in cognitive science and AI, actually, of building theorem provers was from two cognitive scientists, Simon and Newell. There's been a lot of great work by one of my main mentors, Josh Tenenbaum, and others, trying to build good Bayesian models, mathematical models of human cognition. And that's the approach that I'll be bringing to that question of what's going on in mathematicians' minds when we decide what games to play. So I want to focus this talk on this question, how it is that we decide what problems to solve, but reframe it a little bit. We heard nicely just before about how games are one way that we can think about mathematics. And that'll be the lens that we'll start to talk about here. So mathematics and games, as we just heard, are very closely linked. You can think of the axioms of mathematics as defining the rules of the game, the moves that you can take in a game connected to different approaches in mathematics and strategies. There's a long history with mathematical game theory that ties into mathematics. Even thinking now to Kevin Buzzard's Lean tutorial is framed as a game. And I don't think Tim will talk about this in his talk, but Tim, Freider, myself, and some others at Cambridge and MIT have been designing a new game that we hope can help us study how people come up with proofs in a more amenable way to folks who are not as trained in mathematics as you all. But mathematics and games are also closely linked, even in the context of classical fun games like tic-tac-toe. So imagine you all raise your hand if you played tic-tac-toe, or also called noughts and crosses in the UK. OK. Everyone? Raise your hand if you've played 3 in a row loses, the Misery version of tic-tac-toe. Probably? OK. What would be your first move if you were to play this game for the first time? Your task was going first. I'll let you think about this for a little bit. Center? OK. Would anyone do something other than center? No? Mostly center? OK. Our model has a center bias, so that is good. But you can kind of think about games that you've never played before, where even we're just changing one rule. We're actually just flipping the goal. Or raise your hand if you played this game, where it's 3 by 3 in a row wins, but you can only win if you play diagonally. Anyone? No, so you've now not played this one. So people are able to think about these kinds of games and figure out what they might do, whether they're worth playing at all. Sorry, my slides, it's hard to see here. And what this talk will be about is how games can offer a nice window into which we can understand mathematical reasoning in both human minds and machines. So the structure of this talk will be, I'll first talk about some of our cognitive science work, looking at how people decide whether a game is worth playing at all, going into some of our modeling results and human studies there. I'll then talk about how this also informs how we even take actions in the first play. So as whoever just said, kind of going center first, we have a really big new data set that we'll be releasing of how people take action in a wide range of these novel games and also decide when to stop. One of the key aspects of research mathematics, or any research in science or otherwise, is also deciding when it's worth taking a break from a problem, maybe going to solve a different problem and coming back. What is going on in our heads when we do that? Then I'll talk a little bit about some early work on how people create new games that others might find fun to play. I think this ties in nicely a little bit to creating new rules and new concepts, which people are able to do flexibly, and current models can't necessarily yet, but I think language models also are a nice way to help with computational cognitive modeling there. I'll then talk a little bit about some new work that we have ongoing of trying to understand interestingness, as Mike was saying, of math problems and how IMO participants judge whether problems are interesting and how everyday folks do as well. And then at the end, I'll talk about some looking ahead visions that I've been thinking a lot about, which is how can we actually build joyful mathematical AI thought partnerships and thought partnerships overall. As we heard, AI is progressing really, really rapidly. And I think this is a great venue to think about what it is that we're even trying to build in the first place. So a lot of the focus on game playing in cognitive science and AI has focused on human expertise. A lot of the cognitive science or neuroscience literature that you might read really focuses on experts, how it is that experts move their eyes when they're kind of assessing what problem to take or what move to take, or how we can search deeper as we do more plays of any one problem. And this is great and revealing for how it is we could build more human-like expert models, which I think is probably of interest to many of you. But it doesn't really tell us how it is that people start to play a game, how we go from being a novice to an expert. And similarly, in AI, there's often a big focus on kind of machine expertise, not really that early stage, which if we want to get to general purpose problem solving, flexible problem solving to new problems, we really need to understand that first step. We don't start as experts. You might have good intuitions. What are those intuitions that you all might have had in mathematics or other areas that you've been passionate about? How do we reason about new games that we've never played before right out of the box? So this is work that you can't see all the names, I think, but led by Said Zhang and Leo Wang, now Barbara, Graham Todd, and others that we've been working on. We have a preprint of part of this on arXiv, and then we'll have a bigger one on arXiv in about a month. We were very interested in how it is that we decide, as I said, whether games are worth playing. So I'll let you think about this game for a second. Now we're on a 5x5 board, and you are tasked with thinking about whether this game would be fun to play. So I'll let you think for about 10 seconds. Raise your hand if you think this would be very fun to play. Fredder thinks this would be fun? OK. Does anyone think this would not be fun to play? OK. Other folks? OK. So maybe, Fredder, if you thought a little bit more, you would kind of simulate forward what might happen in this game. Maybe the second player goes there. Then maybe you go here. Maybe they go there. And then you go, oh, OK, you go here. If you do this a few times, maybe you just need one rollout to convince yourself, or a few. You might then realize this is probably not actually a very fun game to play. If you're playing against a good person. If you're playing against a young kid, maybe it would be more fun. So then you can ask yourself different questions. Should you spend more time learning this? Would this be a rewarding game to bet on? We spend a lot of time as a collective society betting on different games. Would this be fun? Should you become an expert at this? And these are the questions that you all might have asked yourself when you were deciding what field to specialize in. We ask ourselves these questions all the time. And there's been far less work in cognitive science, AI, trying to understand all of these. So we're trying to take a first step. In one way that we can go about assessing this is by designing a big data set of new games. OK, good, you can see. So what Said and Leo really did was design about 121 new games that varied in board size. So we had kind of 5x5, and these were all variants off of tic-tac-toe or Connect 4, where you've got 5x5, 5 in a row wins, different rectangular boards, other board structures, infinite boards. They also varied the game dynamics. So one player, say you're playing the same game, but one player could go twice on their move. Other kinds of changes in the rules, and then varied win conditions. So as I mentioned, flipping the win condition, so the first player who gets 3 in a row loses. Only diagonal wins allowed. Other cases where players have different kind of pieces in a row that they need to win. So this formed a big data set of 121 of these novel variant games that people likely had not played before, models had not seen before. We are going to release this data set. We're also careful that we don't want people to necessarily over-optimize on this right away, because we are testing models against it. And with this data set, we then asked 3 we're calling intuitive theory of game questions, which is how likely is the game to end in a draw? If the game does not end in a draw, how likely is it the first player wins? So this can form, you can compute an expected payoff from these questions. And then how fun would this game be to play? And we ask the first two questions of one group of people, and then the second question to a different group of people to get at how people evaluate games. And from this, our key question was then, how can we actually model what's going on in people's heads? What is the backbone of an intuitive theory of games that we might have that lets us reason about, get started playing these games and evaluate whether we should even play them at all? And the way that we thought about modeling this is by reflecting on a lot of other work on how people play games, which varies the search depth and also how people choose what moves to play. So as you all likely heard before and have known that a lot of progress is made in Go by doing deep search with either random or learned features. Conversely, there's been some other work in Nature that was looking at how experts play by reasoning about depth 5. In there, they had 4x9, 4 pieces in a row wins as their single game that they did a very deep dive on and used a set of handcrafted game features, but their model does not extend to a wide range. The same features that matter for 4x9, 4 in a row wins likely do not matter for 3x3, 3 in a row loses, or 5x5, 3 in a row loses. There's also been some earlier work in CogSci looking at, in this case, more novices, young kids, of what they care about, of kind of caring about whether you're likely to win by taking a move, make progress towards your goal, offense, versus block, say, by defense. And then at the other end of the spectrum, you've got a fully random agent, which is doing no search and just uniformly choosing a move. And so where is it that novices in our intuitive theory of games live on this spectrum? Our hypothesis is that it's somewhere in the middle here, kind of a case where maybe it's no search or limited search that people are doing when we reason about games for the first time, plus some kind of general purpose gameplay features. So say you might be thinking about how you could make progress with your move versus block the progress of opponents. What we heard a little bit about energy efficiency. If we're modeling how people reason, we need to really be careful and think about the energy costs of what we're doing, or what the model is doing, and also how it is that people might make these judgments before you've actually even started to play. So we're calling this the intuitive gamer model that kind of captures some element of people's intuitions. And there's a few key components of this model. One is that it's probabilistic. This went too far. One is that it's oops. I think this is glitching. I'll just leave this up. One is that it's based on probabilistic mental simulation. So we're thinking forward. Some people might reason about new games without actually imagining how play would happen. But if you can force people to spend at least a minute thinking about the game, we think that people are doing some kind of forward simulation, that these simulations are fast, as I mentioned, that they're flat, that they're doing very depth-limited search, either no search at all or just one step, and that it's goal-directed. So we're thinking about the goals of the problem and how our action might block the progress of another person's goal. If you think about this, and this is a figure made by Leo Wang. So if you, say, are presented with a new game expressed in language, our intuitive gamer has both an agent model that can kind of simulate play in that game, and then a reasoning engine wrapped around that can then make assessments off of the game gameplays that are done. So there's a few key components that we have essentially depth 1 search here, where we're imagining that an agent just does one step forward and assesses what moves are likely worth taking, and that this is done by assessing whether you'll make progress towards your goal with that move, how it balances, might block the progress of another person's move, and also potentially some other features that maybe you care about playing in the center, or if we're thinking about mathematics, maybe you have other heuristics that you care about when you're deciding what action to take, say beauty or interestingness. And then we also posit that there's, you can't see the K, but very few simulations or rollouts that people are taking. I'll give some indication of all of these, but in computational cognitive science, we really need to then dig into each of these claims, which is what we've been doing. So I'll now show you what the results are. So we had 480 or so people reason about these 121 new games. Half of them saw those questions about payoff, as I mentioned. The other half saw questions about funness. And what we see is that if you run simulations forward in that model that I mentioned, the intuitive gamer model, we actually get a very good fit to people. An R-squared of 0.8 is quite strong for modeling human judgments in cases like this. The error bars are the 95% confidence intervals. Here, our goal for at least the next few slides is modeling people. But as you may realize, people are also not necessarily good at estimating the exact payoff of these games, as I'll show in a moment. So for now, we care about modeling people. You might then wonder, how do other models do, either models that reduce search in that spectrum of models that I was saying, say random agent, up to MCTS with deeper search. And you also might be wondering how different LLMs do. So we've been looking at this. MCTS is not. OK, there it is. I think for other speakers ahead, I think that there might be a little bit of a glitchy thing here. So you see that our model substantially captures human judgments and variation better than alternatives. There's definitely some oddities kind of with some of the language models and their judgments to people. There's, say, for llama, this is also, we did chain of thought prompting for all of the language models, and also a temperature of 0.7, because we use the default. Yes?
How do you tell the description of the game to the model? Do you give a sample games?
Great question. We give the description, and we gave the same instructions that we gave to people.
Did you make a test of whether it understood that, like play the game? Or?
We haven't tested them on playing the game. Many of these are sensible. I'll focus a bit more on some of the failures, but it does seem to understand the games in many, though not all cases. But I think so the top row are some of the more classical baselines that we would compare people against. We see that people are not reasoning randomly. And again, they're reasoning about the game. They're not actually playing the game in this case. And they're also not doing something like depth 5 search. But the models are also doing something seemingly different. So you might then wonder, how do the models compare? Are they similar to each other? We are correlating here against people. But we also can ask how these correlate with each other. So we had run, this is a wider range of different models that we were looking at. But you can kind of see that this is a correlation matrix on the full data, not doing bootstrap sampling, and that the language models are doing something all much more similar to each other compared to the other models that are either doing some kind of explicit search. We had also compared against a depth 3 model. MCTS and expert are also explicit search, and then random is not. So I think this is pretty cool. So there's some structure that we're seeing in the language model predictions for these games that is different from people and different from these other explicit search approaches, even for something like R1. The R1 is actually a little bit less correlated with some of the language models, so that's also probably telling from the approach. But I also mentioned we had these kind of 3 key desiderata as part of the mental simulations. Just briefly on why we have some further evidence for some of these. So for the fast, we can also run our model to either full game. So if you imagine an agent that's simulating forward how they might play in a game, you could either play all the way to the end in those 5 simulations, or you could stop early with some probability. And we see that generally, if you do some kind of early stopping, that also will better capture people. Because we don't think when people are reasoning about these games, or say deciding what math problem to solve, that you would fully solve the problem repeatedly all the way to the end. You'd probably do a little bit of a think for what that problem could be like solving it, and then take that as your response. And also we see that the goal directedness really matters, that if you ablate any of those components in the value function I mentioned that our model uses to assess states, say progress towards your goal and whether you'll block the other person's progress, the fits to people dramatically fall off. And the dashed line here is the noise ceiling from people. So if you correlate people with themselves, that gives you usually an estimate of how noisy the human data is. So that's kind of a nice noise ceiling for your models. It's as close as we can get to kind of how good our model should be able to be, and we're essentially at that with the full model that we've proposed. But you might be asking, how does this compare to cases where we actually have the optimal game theoretic value or close to it? So of our 121 games, we have 81 that we either have the known game theoretic payoff based on other work, or have used whether MCTS as our approximate oracle has converged, which might be incorrect in some ways. If any of you want to help to figure out the remaining game theoretic values that we are missing. We would be very, very interested in that. Some of these new games we think don't have a clear solution yet, so we'd be very excited to discuss that. What we see is that if you look at either people or the human is the one in black, that people and the intuitive gamer, our model, are not quite correlated with the actual game theoretic optimal. There's many cases where people are not at the optimal, as we'd expect. They've not seen these games before. What we also see is that some of the other state-of-the-art language models are also not. There's many cases where they are aligned, but also a lot where they are not aligned with whatever the game theoretic optimal is. So there's some way to go, likely in having these models to reason about these games. And I think games is a nice way, these kinds of games, to study these models, because it's a way to look at some aspects of mathematical reasoning in a much more controlled setting. And these are evaluations about the game, not just gameplay. As I mentioned, though, we also had people judge whether games are likely to be fun. This can tie into mathematical interestingness and other evaluations we might do about problems that are kind of more of the ephemeral and have minimally been modeled in cognitive science so far. This is also big credit to Said Zhang for doing this. I'm just going to walk quickly through, for the sake of time, these results. But we looked at what features could be read off of our intuitive gamer model that could inform or might relate to human funness. So one idea, or one thing you might think about when you're assessing whether a game is fun, is whether it's likely to be balanced. How likely is it to end in a draw? Does the first player have a big advantage or not? You might want to play a game where there is a definite winner or loser. When I was talking to my mom about these games, she said she'd only play a game if there's an actual loser. So we have a measure that assesses, kind of using Earth mover distance. You can measure the distance between probability distributions between a case where player 1 and player 2 have equal probability of winning, and a draw is extremely unlikely. So if you then compute this over the simulations under our model, we end up with a non-negligible fit to the human data, but certainly not all the way. So there's something else that people are doing when they're assessing funness that's not captured by that. This is also the normalized EMD, so that's why the scales are odd. And that's the average human value for each of those games. You also might think about whether a game is likely to be challenging to play, so not just whether it has a balanced outcome. And here, the way that we computed challengingness is by running the intuitive gamer model against a random agent, so looking at kind of what the value of thinking is by seeing how often the model would beat a random agent. And with any of these questions, we then need to think, how can we actually translate them into operations on this underlying model? And then also say how long the game might take. So this is the scaled length under the intuitive gamer model. And you can see that there is some relationship, but not that strong, between funness and length under this model. But then what we do is we then combine this regression model on these different features, which might capture at a computational level how people assess different features when they're thinking about whether games are likely to be fun. And then we get quite a strong fit. The noise ceiling here is much lower because people are quite variable. Not everyone has the same ideas of whether a game is likely to be fun or not. So this is about at the noise ceiling. Yeah.
This is all the initial guess of whether the game will be fun?
Yes, initial guess.
And did you try to let people play the game a bit and then revise their?
Yes. So that's new data that we also have. Yes. So this is all, again, all of this so far has been before someone actually plays a game at all. And we're trying to model what is going on when they make those judgments. And what we end up seeing is that it does matter. The novice here is the intuitive gamer model. That you do want to do those simulations under the intuitive gamer model, that you can get some fit from the other models, but not as strong. So these are simulation-based, and then these are some of the just feature-based that we computed over the game descriptions alone. But I'll just kind of go through this for the sake of time. You might then be asking what the LLMs think are fun of these games, how that relates to people. And a Friday sent me a Slack message asking me about how the LLMs do earlier today. And what we see is that GPT is remarkably well correlated to people, that we've been a bit confused why it's so much different from some of the other models. And if you actually combine GPT with those other model-based features, you can get a really strong correlation. So GPT is definitely capturing something of the human funness that our model is not yet. That ultimately makes sense that part of what we decide is fun might be based on the language, the linguistic description, linguistic quality, how those relate to whether we've seen a game before. And also, our model isn't really capturing nonlinearities between these components. Yeah.
These are all like one shot, where did you try giving the model some examples and then asking?
No, this is all one shot. We are very interested in how do these models do in essentially the same conditions as people.
Well, but people have played games, and the language models may be less fun.
Yes, but the language models have also seen millions of games more than people to some extent. There's
I'm sure there's so many games that people find about. But anyway.
That's true. That's true. Yeah. So there's other ways we could certainly prompt these. We should definitely not take this with a grain of salt. And we see that there's again some structure across the models. I was very surprised to see that Llama 70B and DeepSeek R1 were extremely correlated. Need to check that more of what is happening there. Maybe some of the meta folks here could explain that. But I think, yeah, there's a lot that's interesting that can be looked at with these games. And I'll just show a few examples to give a sense of comparisons to people. So first, think about I guess this is shown already, but the game 5x5, 3 in a row wins, where the second player can place 2 pieces on the first move, and the first player can only place 1. This is a case where the models all had a higher average funness score, whereas people were much lower. People also have tic-tac-toe at about 50, which was kind of fun to see. We had everyone respond for tic-tac-toe. And then we'd also, as I said, presented infinite boards, and this is a case where there was actually some disagreement across the models. Both R1 and Llama, in this case, thought this was a medium, a little bit less than average. GPT and DeepSeek V3 were not as happy with this particular game. People were also about 40. So I think there's a lot more that could be looked at of how these models assess these kind of other judgments like funness. So as a summary, our main, we have now k equals 5 simulations. We realized it's actually seemingly less than 20 in the fits. But as, okay.
That's a question, yeah. Do these games also have chance? Are they random also, or is it only decisions?
Only random in the games.
So is there like dice throwing, for example?
Oh, good question. No, these are all kind of MNK style games, where then in 2-player MNK games, where
what does that mean?
like the board size, and then and then K in a row to win. So they're all that structure, and then we change some of the rules where some player sometimes can get by with K minus 1 to win, or another player can play 2
You
moves.
didn't try with chance games?
No,
Okay.
no, that's a great question. There's a lot more games, which is also why we're hesitant to call this an intuitive theory of games, because it's a intuitive theory of a very small subset of all the games people play. So a lot more to do. Yeah. But a big question you might have with all of this is then, how is it that we also play in these games that we've not played before? Our kind of intuitive game reasoner that's judging these games also nests in it a model of gameplay by kind of forward simulating. So our next set of experiments was to try to understand how people actually play in games. We had about 320 participants that each played each other in 6 different games, where one of those was always tic-tac-toe, and they play this against the same opponent. So you were kind of, and importantly, we also gave people the option to either request a draw. If someone requested a draw, you had the option to also reject or accept that draw. So this gave us a chance to look at how people stop and make those decisions potentially together. And you also had a chance to surrender. This data set totals over 900,000 moves, choices that were made. So it's one of the biggest gameplay data sets that we believe has been collected before. And it's over a subset of 40 of the 121 games. So I'll just briefly go through some of the results for the sake of time. If we then fit or compare the intuitive gamer in red model to some of the other models that vary in either increased depth or random, that this is an aggregate. So it's nicer to look at when we have sub games. But generally, we see that across many of the games, most of the games, the biggest component is the intuitive gamer best captures people's play that they did. And this here is fitting an admixture model. So it's assuming that any one person's move in any game is, with some probability, played by one of these different agent models. And that's a way to give a sense of how much any one model best explains those games. Any way that we also had people watch games and then reason about them. We had another 300 people do that. And across both of the studies, any of the win inversion cases, when you have people reasoning about games where the first person to get K in a row loses, are actually very hard for any of these models to capture. People are best fit by random, but if you look at the way people are playing, it doesn't seem like random. So that's a good failure case of our model. You might also wonder, well, people differ in how expert any one person might be. Some people are more naive in their play than others. I actually have very bad intuitions about some of these games, so I'm in the more naive category. We can also do these admixture fits at an individual level, and generally, again, see that kind of play under the intuitive gamer model best captures what people are doing. But as I mentioned, we gave people the option to request a draw or surrender, which gives us a sense of how people decide when it is to stop at all in a game. And this can connect to in mathematics when you're deciding whether you should keep solving a problem, stop, go back to a different problem. This kind of data can help take baby steps into that direction of modeling that. So here we were this is all exploratory analyses, thinking about maybe someone is actually, when they're deciding whether to accept or reject a draw. So you're given imagine you're playing these games, you're given a draw request, and you have to decide whether to accept the draw request from the other player or keep playing and reject it. That part of your decisions around that might be thinking, how likely am I to win? What's the expected utility of this game? We had people, if you won, you got a bonus of 50 cents, and if not, you got nothing. So you might be assessing utility based on that bonus payout, as well as thinking about the expected game length. So if this comes early in the game, is it going to take you 100 moves to win? In that case, maybe you'd be OK taking the draw and stopping and going to a new game. You also might think about the funness. So what we see is that generally, if we then fit, we only had about 140 of these cases where this happened, so limited data. But if you then fit a logistic regression model based on to predict the probability of accepting, where red here are the regions of space where you're more likely to accept a draw versus reject, we see that generally places where someone thinks they have an high expected likelihood of winning are going to reject the draw. But that there's some cases, say if the game is really fun, that maybe you're OK to reject the draw and keep playing even if you think you might lose. We can then do that same approach for all the other models that we have. And generally, you see that if you ablate different components of the value function, say having a player, simulating that a player is only playing offensively or only playing defensively, that the fits kind of collapse and we're not as well able to explain the data. I think that the case of only defense is especially interesting. So that's if you're only, you ablate the offensive component, because if you're presented with a decision to reject or accept a draw, you might be more in an offensive situation because you know the other person is somewhat at a weak point because they've said, do you want to end in a draw? So ablating that component really seems to hamper performance. And this is starting to address the question that Mike gave, which is, well, the funness results that we presented were before people had ever played the game. Now we have people play these games. How does the action actually influence people's judgments? And here we're also inspired by a work that I know Mike has referenced in his talk before of kind of immediate versus evolving evaluations of problems, that we can judge problems before we encounter them, and those judgments also might change over time as we're solving the problem or afterwards. And what we see from early evidence is that, one, people are influenced by the outcome. So here, this is a density plot of the funness judgments based on what outcome that player had before they gave their judgment. That we see that even in cases where you lose, a lot of people were still rating the games as quite fun, but that the cases of more when you ended in a draw, there were more cases where people were finding that less fun, which also ties into balance. You can see a little bit of shift, but it's not that strong. And we can also then fit these regression coefficients to the data from just the think data, as well as the post-play. And while all these features do seem to matter, there's different gradations of how much any one of these features seems to matter. So people might be thinking about different things or different properties of the game when they're judging them after playing. Yeah, so this is we had people after each of the 6 games that they played rate the funness of that game, and we said rate it overall, so not just that match, how fun was that match, but that game. And then we can separate out the judgments based on the outcome of the actual.
I would look at the variance of whether you win or lose.
The variance of whether...
If you don't always win, you don't always lose.
Yes. Yeah, that's a good... Yeah, there's a lot more that we can look at with this data. So just to summarize this kind of intuitive theory of games idea is that when we're thinking about these new games and playing in these new games, we're doing a mix of both kind of simple, fast, goal-directed judgment of board states, and then nesting this within some kind of probabilistic approximate expected value computation or other readouts on the funness model. And I think some of these ideas of when do you search deeper or less? What kind of features do you care about for problems that you've never encountered before? Could also apply to how we think about new ways of building models. And as mentioned, clearly there's something else going on with some of these language models than people or explicit tree-based approaches. So there's a lot that we could also learn about language models here. For the sake of time, I'm going to really quickly just click through a few other work that we're doing, which is those 121 games are human created to an extent. Sed and Leo made a lot of them. But we can also, you might be thinking in your head about other kinds of games that you would want to play of this kind of two-player grid-based variety. So we have a new set of, and there's also a lot less cognitive science work understanding human creativity at all. And that could be what we need to understand with LLMs of how we can get them to get better at generating new games. So we had people actually at the end of that study that I was showing where they were thinking about these games to then, once they saw the 10 different games that they'd played, to then we tasked them with creating a new fun game. And we have now 480 or so created games that people had made that we can then try to model what's actually going on in our heads when we're creating these games. I'll let you look at these for a little bit. Some people were going very heavily based on what they saw, which is also interesting. Part of creativity is also deciding what to even combine and what you'd seen. It's not always inventing entirely new concepts, but certainly some other people did invent new concepts. For instance, this person saying that they want to play 10 by 10 where you have to get 4 in a row and yell floofy if you win, else it doesn't count. That might be perhaps a new concept, though maybe not one that we want to optimize for with models. But some of these are quite creative. We saw a lot of kind of making shapes, L shapes, zigzag shapes, that was not in our data set at all. So people we're going beyond that. And we'll have this on arXiv. It'll be at CogSci, the CogSci conference in San Francisco in July, and it'll be on arXiv very soon. But now I want to make a brief pivot for about 10 minutes from fun games to thinking about interesting math problems. And here, Mike has a really great talk that I know he just referenced earlier, where he also talks about how we can get computers which can judge interestingness. So we are inspired by that. And this is great work that's led by Yuka Machino, who is a recent MN student at MIT, who I believe is starting a PhD at Stanford very soon. At the IMO last year, she went and she asked participants there to judge the interestingness of a set of IMO problems. So she got about 61 participants at IMO last year over about 33 different problems. And she asked them to rate different dimensions of interestingness that she's also IMO level mathematician as well. So she had thought about different dimensions of interestingness that matter to her, and also looking at literature, had them rate different dimensions that mattered, and then score a set of these problems on how interesting and difficult they were. We are in the very early stages of analyzing this data, and with a bigger team as well. I'll present a few tidbits into the data, caveated that one of the challenges with why we've been a bit slower to analyze the data is that there was a batching problem. So many people saw only one, or many problems of the 33 are only rated by one person. And then there are several problems that were rated by a lot of people. So we are likely going to need to recollect a bunch more data for this to get actually good grounded data. But already what we see is that there is, we can then look at, so each of these points is one person's response for one problem. There's not a super strong relationship between difficulty and interestingness. Again, this is also with IMO level participants. So what they might deem difficult is very different from, say, what I might deem difficult of these. We can start to look at a relationship like this. And also what Yuka had nicely done was ask people, when they rated the problem, what factors mattered for them, for that problem to be rated as interesting, which is in blue here, or not interesting. So what we see is that there were more cases, and then the relative frequency on the y-axis. For the cases of why someone found the problem worth rating interesting, that the problem is simple or elegant, as you might imagine being interesting, that it doesn't require particularly sophisticated techniques to be able to solve, that there's kind of not a big challenging set of strategies to be able to get there. Conversely, for some of the things that made a problem not as interesting would be that the techniques required to prove it or the ideas are too standard, that the proof statement is itself unnatural or contrived. You had given people the option to either just rate them without seeing the solution or to see the solution before they rate it. So we also need to look at that in the data. I think one thing I'd love to talk to any of you in the coffee is what also matters to you when you're deciding whether a problem is interesting. I'll just show two brief examples from the data set that we have. So this is one problem from 2021 that had some interesting judgments. I'll let you look at this for a second and think about whether you would find this problem interesting. Do folks say on a scale of 1 to 7 if you're shaking your head no, this is not an interesting problem? OK, some folks, yes, interesting, not interesting, not interesting. OK, well, the IMO participants who did this, generally, most people rated this as actually somewhat of a difficult problem, and interestingness being actually quite high on the scale of 1 to 7. So it's different from you all, which is also, I think, there's different levels of expertise. You've got folks who have not encountered an IMO level problem before, up to super expert superstars. So this is what we got from the 4 people who saw this problem. And then here's another problem from 2021 as well that we had 2 judgments on for this. I'll let you think about this problem, whether you would find this problem interesting. Would anyone find this problem interesting? Yes? Anyone find this not interesting? OK, another not interesting, not interesting. OK, so what we see here is that people were, there were 2, this is kind of a bimodal response case. We only had 2 responses. Again, we need to collect more. One person thought that this was actually somewhat interesting, but they also found it very difficult. Maybe they didn't really understand the problem, and that was why they rated it a little bit more interesting. Another person thought this was not difficult at all, and they were not enthused whatsoever, and they rated it a 0 on interestingness. So we need to do more here, but I think these kinds of directions are where, as Mike was saying, it's worth not thinking only about how we solve problems, but actually how we judge problems in the first place. And I think this kind of data can also form the bedrock of what we might hear Frieder talk about, which is what new kinds of data can we collect about mathematics to build the next set of copilots. And even also just better understand mathematical reasoning in people more broadly. We're also extending this to the context of everyday interestingness. You all might be above the IMO level, but there's also kind of what is going on in our heads when we rate or judge math problems before we've even reached IMO level. What components matter and how can we simulate them? How might we adjust this? That you might be thinking as you're trying to solve a proof. Maybe you're doing some kind of back and forth where you're thinking about kind of progress towards proving versus how you might set up a counterexample that can block progress of yourself. Or maybe there's something else entirely, and we actually don't want this kind of goal progress with goal opponent. You might then just be thinking about your own progress towards the goal, not imagining another opponent. So I think that'd be interesting to discuss. And then what changes as we develop our mathematical expertise. This also could be used to then train a next set of intelligent language models or other AI systems. And that's something that Gabriel Puesia, who's involved in this work, had been doing, where he kind of endowed some models with a form of curiosity or exploration that then was used to bootstrap its ability to train on new math problems. So hopefully that you might have seen this kind of whirlwind tour that there's a lot of synergy between computational cognitive science and of games and mathematics. We have another paper on arXiv where we start to explore some of these ideas. I think that this is a really fruitful 3-way connection, not just between AI and mathematics, but also cognitive science, because there's a lot that we can learn still about people, how it is that you all are reasoning. And I'll just end by stepping back a little bit, that this conference is awesomely titled Mathematics for LLMs by LLMs. But I hope that we all think as well as not just mathematics for LLMs and by LLMs, but also mathematics for humans, by humans, with LLMs and other AI tools. That mathematics is really something that humans have been doing for centuries. It brings, hopefully, many of you joy, fulfillment in what you're thinking about. And I think we really need to think about how models can actually move towards us. I think we really need to think about what we're trying to build. So we have some work trying to think about how it is that we might build machines that learn and think with people across not just mathematics, but more broadly, what it is that we might want. We might want models that explicitly reason about our beliefs, what our goals are, how that can inform different kind of suggestions. Maybe if you really love a certain aspect of your mathematical discovery process and you just don't want to do the formalization part, maybe we could design a system that can still let you do things that are joyful to you, but then automate away other parts that maybe are less fun in your work. Also, things as we talked about with funness, it also is helpful to have things that are challenging. So I think balancing what we're automating with things that bring us fulfillment and joy is worth doing. As I think one final case in point is that we also haven't stopped playing games now that we have superhuman AI. I think this is also one possible optimistic future for AI in mathematics, that some great researchers from Tom Griffith's group and beyond at Princeton looked at how people's Go playing strategies have changed since AlphaGo, and they found that there's quite an influx in people's certain kinds of moves, that people are doing new moves now that AlphaGo has been on the scene, what might that look like in mathematics? What kind of new moves might you all be doing if these models really do keep improving at the rate that they are? So I just want to end with reflecting that mathematics really is an art. I think I really loved G.H. Hardy's book, A Mathematician's Apology, in the quote that mathematicians really are more like painters and poets. And I think there's been a lot of progress in formalization because we can kind of check whether solutions are correct or not, which we haven't seen as much in, say, automating. These models do poetry quite well, but I think there's sometimes we can think, or someone who's not as trained in mathematics might think that mathematics is just about automating how we can scale up done in terms of proofs that we might generate. But there really is an art of kind of beauty and interestingness of these ideas that I think we should not forget when we think about mathematics for and by humans with LLMs and these tools. So thanks to the organizers for this.
Questions?
Yeah. Did you try, I mean, I don't know if there's some concept of information for a game. In other words, perhaps something has to do with the number of rules as opposed to how many games you can play with this kind of rules, you know, some sort of economy. And does that exist, and did you try to quantify this somehow?
That's a great question. We've not tried to, we've started to try to quantify that because one of the things I mentioned, GPT is doing something different with its funness judgments than any of our model-based features and also some of the other LLMs. But people might be accounting for the structure of the rules that we're not capturing in our model-based measures. We've not looked at that yet. But that also could be something maybe to think about with some of these games that could help us get towards more of the game theoretic optimal for some of these.
Maybe you said, did you measure the correlation between people's initial guess and their later judgment of funness?
Yes. Yeah, I didn't put that scatter plot up, but it's about 0.45 R-squared. So there is some shift in people's judgment, partly from, we think, the actual outcome, as well as other features that seem to matter to people after they've played the game. They realize, oh, actually, I'm OK playing a longer game if it's going to be fun.